So we left off in the first video on gases with the ideal gas law and using it to solve one of the four variables, pressure, volume, temperature, and moles. Let's take that idea and continue focusing on it using PV equals nRT to solve some other ideas as well. So here, for example, we can get to mass, we can get to molar mass, or we can get to density using PV equals nRT. So just a reminder, molar mass, in this case we're just going to give it a capital M, is equal to mass per moles, grams per mole. So we're going to take that idea, since moles is in the ideal gas law, we can take this equivalent, manipulate it so that N is equal to grams divided by molarity, mass divided by molarity. Put it in PV equals nRT, and we can get an equation like this out of it. So if we manipulate this, we can get to molarity, molar mass is equal to mass times R times T divided by P over V. The other idea that we have is the idea of density. If you recall, density is mass per volume. Well, we've got moles and volume here, so we can once again take this idea, manipulate it in order to solve for, or in order to incorporate density into the idea. So mass and molar mass in here instead of moles lets you express the ideal gas law kind of in a version including density. So this slide now has a couple of sample problems to do, so please feel free to stop and try it on your own before you take a look at the answer. So first question deals with density. We've got room conditions of 1 atm and 25 degrees Celsius. What's the density going to be? Well, the equation that we want to use is not PV equals nRT. We want to manipulate it a little bit, get the molar mass in there, and express it so that we've got an expression of density. So plugging in the numbers the way we have it, we can solve for a density of 1.31 grams per liter. Second kind of question, again, stop it to solve it before you take a look at the answer. We want to know what the molar mass of a substance is given conditions of temperature, pressure, volume, and mass as opposed to moles. Well, hopefully you can see it's a quick jump to get from PV equals nRT and solving for moles to grams. And that'll let us get to molar mass. So molar mass is equal to MRT divided by PV. Plug in those numbers, we get a molar mass of 64.1 grams. Now again, you don't have to memorize these new versions of the equation. If this doesn't make sense to you, solve PV equals nRT for moles and then consider what the equation for molar mass is and manipulate it that way. So there's any number of ways that you can sequence this work. Last question. You've got density of a gas at a certain temperature. We want to know what the pressure is going to be. Once again, stop it so that you can try it yourself. At least manipulate the equation. That would be good. So we're solving for P equals nRT divided by V, but in this case, we need to take that mass that we have, so we got mass per liter, there's our density, and convert it into moles per liter. So I'm going to use my molar mass there, and R and T obviously gives me a new pressure of 1.27 atms. Alright, so last idea, whoops, animation didn't work quite so well. Last idea is taking some other ideas of stoichiometry into gas equations. So in order to do this kind of stuff, you have to have an actual chemical equation that involves gases. So the first idea is making use of that standard molar volume. You learned that at STP conditions, 1 mole of gas will occupy 22.4 liters. So at STP, here is a relationship that lets us get back and forth between moles and volume. So we're going to use that to our advantage. Like I said, it's an easy way to convert back and forth. Please note that this does not work if you have something that is not a gas. A liquid or a solid does not abide by this relationship. Only gases abide by this relationship, and only under standard conditions. So you've got to be very careful. If you don't have standard conditions, you've got to go back to solving for PV equals nRT to get back and forth between moles and volume. The other idea that comes up is the idea of volume ratios. So under any condition that is constant of temperature and pressure, you know that the number of moles is proportional to the number to the volume. As the number of moles goes up, the volume has to go up as well if we're going to maintain constant temperature and pressure. Well, you can then therefore not only establish mole ratios from a balanced equation, but you can also establish volume ratios. But again, this is only for gases. So here's the equation that these two ratios are coming out of. So here's the traditional mole ratio that you know, 2 moles of ammonia for every 3 moles of hydrogen gas. But since they're both gases, under the same conditions, I can establish a volume ratio as well. So here's a sample problem, or several, to let you do that. So again, read the question, stop it, give yourself a chance to try and solve it. So what volume of ammonia will be generated from 6.81 liters? So we can use that volume ratio that we saw on the last slide, and I can get 2 liters of ammonia very efficiently from liters of hydrogen. I don't have to use PV equals nRT or anything like that to get 2 moles first. I can go right to a volume ratio because they're both gases. Second idea, I've got a chemical equation here. It's happening at STP, so we want to know how many liters of oxygen gas I can get from 8 moles of potassium chlorate. Please notice potassium chloride is a solid, so the order that you solve this problem in matters. So here's the idea. First thing I have to do is take that 8 moles of solid and get it into my gas. So I have to do a mole ratio. I can't do a volume ratio. KClO3 is not a liter. It's not a gas. So I have to use a mole ratio, not a liter ratio. Since I'm at STP, however, once I'm in moles of oxygen, I can get to liters of oxygen using standard molar volume. Third idea asks you, under non-standard conditions, what are you going to have to do? Well, remember, at non-standard conditions, I can't use 22.4 liters per mole. I have to use PV equals nRT. So PV equals nRT to solve for volume. To get my moles, I've got to convert that 50 grams of KClO3 into moles of O2. So molar mass of KClO3, mole ratio between oxygen and KClO3 to get to moles, and then I've got R and T and P. And there you have it. That's the end of the stuff that we had done during first year. So over the next couple days, we'll practice a good amount to make sure that you are comfortable with it.